Section 4.4 Undetermined Coefficients Superposition Approach. In this section, we will use the method of undetermined coefficients to find the solution of the non-homogeneous linear differential equations, where the coefficients ai are constant term, and the gx could be a constant polynomial function, an exponential function, a sine or cosine, or the finite sum of the product of these functions. To solve the above differential equations, we must find the complementary solution, which is yc, and the particular solution, which is yp. To obtain a particular solution yp for the non-homogeneous differential equation is called the method of undetermined coefficient. Step 1, we're going to find yc by solving the associated homogeneous differential equation. And step 2, we're going to determine the function type of the gx, and then substitute the function and its derivative into dA to find the specific coefficient, which is called the method of undetermined coefficient. To get the form of the function yp, we have to look at the type of the gx, which is the non-zero term on the right-hand side of the non-homogeneous linear differential equations. If the gx is in the constant form, the yp will be the letter a or the notation a, and then we're going to solve for a by using yp prime, yp double prime, and so forth. Substitute into the differential equations and then solve for a. If the gx is the polynomial degree 2, the form of the yp will be the polynomial degree 2 with the highest power 2. So we're going to have 3 unknowns or 3 undetermined coefficients as a, b, and c. For the sine and cosine function, for example, sine of 4x or the cosine of 4x as part of the gx, so we form the solution yp as the combination of cosine and sine, even though we have only one term, either sine or cosine, but the yp has to be as a sum of both sine and cosine with the coefficient a and b. The exponential function. For e to the power 5x as the form of the gx, the yp will have it as a or the coefficient a multiplied by e to the 5x. If we have the combination like the product of the polynomial and the exponential function, for the polynomial part, which is the degree 1 or the linear term, we're going to have the form ax plus b to represent that linear part, and e to the 5x as the exponential part. If you have the power 2, as this example, like x squared times e to the 5x, for x squared, that's a polynomial degree 2. That part we will use ax squared plus bx plus c, and then multiply by the exponential e to the 5x, and then determine the values for a, b, and c. For the case that we have the combination of other function and the trig functions, like number 11, we have 5x squared times sine of 4x. We have the polynomial degree 2. So we have polynomial degree 2 as part of the form of the yp, and then multiply by the trigonometric part, which is both sine and cosine. So we have the long terms, like ax squared plus bx plus c multiplied by cosine of 4x plus the quantity ex squared plus fx plus g multiplied by sine of 4x. So in this case, we have 6 undetermined coefficients. For the last case, if you have the combination of polynomial, exponential, and the trig, we look at one at a time. For the polynomial degree 1, ax plus b, cx plus e. For the exponential, same exponential form. For the trig function, it has to be both sine and cosine. So we have 2 separate terms, one for the cosine and the other one for the sine. For case 1, this case, no function in the assumed particular solution yp is a solution of the associated homogeneous equation. So the rule for this case, we're going to form the yp, which is the linear combination of all linearly independent functions that are generated by repeated differential equation of the gx. The first example, y double prime plus 5y prime plus 4y equals 12. Step number 1, we're going to find yc by using the associated homogeneous equation. Which is y double prime plus 5y prime plus 4y equals 0. The auxiliary equation or the characteristic equation will be in the form of m squared plus 5m plus 4 equals 0. And solve for m. Factor completely, we have m plus 4 times m plus 1 equals 0. That gives us m equals negative 4 and m equals negative 1. Therefore, we have the y1 equals e to the negative 4x and y2 as e to the negative 1x. Then we get the complementary solution. As yc equals c1 y1 plus c2 y2, or the linear combination of y1 and y2 as yc equals c1 times e to the negative 4x plus c2 e to the negative x. And this is the case 1, which the solution, the y1 and y2, they are not repeated with the form of the gx. Gx is a constant term where y1 and y2 are exponential form. So this is called case 1. Next, we're going to find yp, which is the particular solution, by using the gx form. Since gx is 12, which is the constant term, and again, this is case number 1. So then the form of yp will be yp equals the constant a. And then we're going to find yp prime, which is 0, yp double prime, which is 0 as well. We claim yp is a solution. Therefore, the solution yp must satisfy the same differential equation. From the differential equation, we're going to replace with the yp term and yp prime and yp double prime. So yp double prime plus 5 yp prime plus 4 times yp equals 12, where yp prime and yp double prime are 0. And 4 times yp, which is 4 times a, equals 12. Therefore, a equals 12 over 4, or 3. Now we have both yp and yc. So the general solution of this differential equation is y equals yc plus yp, which is c1 e to the negative 4x plus c2 e to the negative x plus 3.